Hi, let's talk about some stars and galaxies. Now, because stars and galaxies are so far apart, we need a new way to measure distance. And so what astronomers have done is defined a new distance called a light year. And that's the distance that light travels in 1 year. The speed of light is 300 million meters per second. And then if you wait not just 1 second, but for a whole year, then the light can travel over 10 trillion kilometers. And so a light year is equal to 10 trillion kilometers. Okay, and that's a very handy unit of measure because the nearest star, the very, very closest one, is 4.2 light years away. So that's really far. The nearest galaxy, here's a picture of the Andromeda Galaxy, that's over 2 million light years away. And so even though it's a convenient way to measure light, we also have to realize that it is a measure of time too. Because when light first left the Andromeda Galaxy and came out headed towards Earth, that light leaving the galaxy takes 2.3 million years ago. So what we see of the Andromeda Galaxy is the picture of it over 2 million years ago. So things probably have changed since then, but we're just going to have to wait for the new light to reach us so we can see how the Andromeda Galaxy looks like later in time. The North Star is called Polaris. So as the Earth rotates about its axis, there is one star that's lined up with the North and South Pole, and that's Polaris. And so as the Earth rotates, Polaris stays still, and all the other stars appear to circulate or rotate around that central location. So here's a time-lapse picture of the night sky. And if you want to know where the North Star is, well, you just have to find the Big Dipper. That's a big constellation, also called Ursa Major. And at the very tip of the scoop of the Big Dipper, just take those two stars and they line up and point towards Polaris. As you look at the nighttime sky, you'll see lots of different stars of different colors and brightness. And it turns out the brightness depends on two things. First, the total energy emitted. So some stars are very bright and others are dim because the brighter ones give off more energy. But the brightness here on Earth is also dependent on how far away those stars are from Earth. So you can have two stars that, if you're right next to the star, they appear to be the same brightness. They give off the same amount of energy. But if one star is farther away from Earth than the other one, then the more distant star is going to be dimmer. Okay, so astronomers define something called luminosity, which would be the brightness if you could view each star from the same distance. And then there's also the color of the stars. And the color is related to the surface temperature. Blue is the hottest, yellow is in the middle, and red is the coolest. So you probably have seen something glow red hot like the little filaments inside a toaster. And then something like an arc welder or something really, really hot would glow white hot. And maybe even if it got hotter than that, would be blue hot. Our sun is yellow, and so it's an average star. Okay, and here's a theory about how stars are created and what their life cycle consists of. The origin of a star begins with a bunch of dust and gases just being pulled together by their own gravity. And as more and more gas and dust and particles and stuff, mainly hydrogen, get pulled together, the increase in gravity causes the gases to be pressurized. And as they get pressed together, the temperature increases. And at a crucial pressure and temperature, once it's high enough, you can get the fusion of hydrogen to helium. Okay, fusion is a big explosion, right? So there's an outward pressure, just like you'd have in a nuclear bomb. And so as fusion takes place, there's this outward pressure that pushes outward and causes a star to expand. And yet gravity is still going to try and pull everything in. So there's a balancing point. There's a balancing point where the fusion's outward pressure balances the gravitational contraction, and that will determine how large a star is. Now the star will live a long time burning the hydrogen it has, and as it approaches so-called old age, the hydrogen is going to be depleted. And as the hydrogen starts being used up, well, then the fusion will take place at a slower rate. If the hydrogen atoms can't find each other in all this big star, then it's not going to be able to fuse together to form helium. And what does that mean? Well, As fusion slows down, there's less outward pressure, and now gravity is going to take over and start compressing the star together. And then once the star is compressed together to increase the pressure and temperature, then the fusion of helium to carbon can start up. And it's a several-step process. You have to have two heliums merged together to form beryllium, and then beryllium has to fuse together with helium. Remember that's actually an alpha particle from radiation? Yeah, the nucleus of a helium, 2 neutrons, 2 protons, has to fuse together with beryllium to form a carbon nucleus. And then you get more energy released. And there's another explosion, and there's a huge amount of outward pressure. And now this outward pressure can expand the star to huge proportions and transform the star into a giant star. And so now the star in old age is even much larger than when it was just simply burning hydrogen. The next phase of the life cycle of the stars is death. And there's a couple of different scenarios depending on how big or how massive the star is. How much material, how much mass the star contains. Okay, case number 1A, I guess. If you have a low to medium mass stars. And it turns out, like I said before, our sun is an average star, medium mass. And so as the helium is being fused to carbon and the helium starts being used up, well, the rate of fusion is going to decrease. There'll be less outward pressure. Gravity again will take over. And this huge giant star will then contract to the point at which you can get massive pressures and temperatures so that the last traces of helium will just detonate very quickly. It's not a nova. There's not enough material there to make a supernova or a nova, but it is an explosion that just ejects. It kicks out the outer layers of gases and it forms a nebula. So down here is the Horsehead Nebula. And then the remaining mass that didn't get ejected out, essentially the core mass, will then contract under gravity to form a white dwarf. And that's a very massive star. Not very large, but just has a lot of mass, all packed together in the middle. And, it'll be glowly dimming, and eventually it'll just wink out and just be this big mass of material out in space. Now for low to medium mass stars, most of the material inside the core is going to be carbon. And carbon here on Earth has two forms. It can be charcoal or graphite, but it can also be diamond. And diamond on planet Earth occurs when carbon is subjected to high temperature and pressure. So it's quite possible that the center of a white dwarf is really a planet-sized diamond. Well, here's a second case for low to medium mass stars. Well, sometimes two stars exist together to form a star system. That's called a binary star system. And these two stars kind of orbit each other. They orbit around a common center of mass. And then when one of them dies to become a white dwarf, well, it can use its gravity to pull some gases off of the second star. And if it pulls in hydrogen, well, the hydrogen will then be packed, and when there's enough gas there, it can start nuclear fusion again. And what you get is this burst of fusion that just explodes, and that's a nova. And so very quickly, all that hydrogen that was being collected will just detonate in a quick fusion reaction, like a nuclear bomb, and then the cycle can repeat. The white dwarf can begin to draw in more gases from the companion star until it reaches a critical amount, and it can detonate once more and form a nova. Okay, what happens if the masses are even larger? So if we have a high mass star, well, let's go back to where helium was being fused into carbon. And so for a very large star with a lot of material, as the helium gets used up, well, again, fusion is going to slow down, the outward pressure is going to decrease, and gravity will take over. Gravity will compress all that mass into a smaller volume. The pressure and temperature is going to go really, really high to the point where at such huge temperatures and pressures, you can actually get carbon to start fusing together to form bigger or heavier elements. And that'll just keep on happening until most of the carbon will ultimately change into iron. Now, do you remember those two nuclear processes? One was fusion, where you take two nuclei, the centers of two atoms, bring them together to form one atom. But there was a second process called nuclear fission. And that's where you take really, really big atoms and split them into smaller ones. And it turns out the tiniest atoms release energy when they fuse together, and the biggest atoms release energy when they break apart. So there has to be a balancing point, and the balancing point is iron. So iron is of the right size so that if you try and fuse it with some other small atom to make it bigger, you don't get any energy out. And if you try and break iron into smaller pieces, you don't get any energy out. So essentially it's a dead end. So in these high mass stars, under huge amounts of gravity, fusion is going to take place until most of the material changes to iron. And then once again, fusion is going to slow down and the gravity will take over and make it contract. And now, under these huge masses, the iron core, right, all these protons and neutrons and electrons flying around, they're going to get compressed into a tight, tiny ball of neutrons. So the protons and electrons are going to be pushed together to form a neutron. These large cores of the stars are really going to shrink from the size of the Earth down to just a few kilometers across. And it happens within minutes. And under this extreme pressure and temperature, the outer core is just going to go crazy. And the last bits of fuel, the atoms that are not iron yet, you'll get one last fusion reaction, and that'll be a supernova, and it'll just rip the whole star apart. Just outside the core of neutrons, the energy will just start pounding on the atoms that are iron and push them together to fuse them into heavier elements. So fusion takes place now because there's excess energy, external energy that's going to squeeze the iron together. And so you don't get any energy out of the process, but by putting energy in from the supernova explosion, you can make bigger and heavier elements. And that's how we think silver and gold and the larger elements are created. And so when we find silver and gold on planet Earth, the theory is that those atoms came from supernova that occurred long ago. Okay, finally, the core of these high massive stars that have finished their supernova, well, what's left behind is this ball of neutrons, and you get a neutron star. And it turns out some neutron stars spin rapidly and periodically emit radiation, and those stars are called pulsars. So here's an artist's rendition of a supernova, big old explosion over here. And then here's some relative sizes. We got the Earth next to a typical white dwarf. What happens when a low to medium mass star dies? You just get the white dwarf, essentially a ball of carbon, maybe a big diamond here. But when high mass stars die, the atoms are squeezed together into a neutron star, which is really, really small. And so all this matter, the size of the white dwarf here, all that material gets packed very, very tightly in a small region. And so now the gravitational force is going to be really huge near the neutron star. If these neutron stars are spinning and glowing, they become pulsars. So here's the idea. You got a neutron star here, and it's shooting out a jet of plasma or light, and this whole thing is just spinning. And so this sort of like these spotlights in the sky kind of idea, the light is going to keep moving around the sky. And sometimes the light will be directed towards Earth. So in the Crab Nebula, there's a pulsar, and here you can see the pulsar directing its light towards us, and then later it's not. And so these little stars seem to wink on and off. Here's another picture down below. Yeah, the idea is that they're not turning on and off. They're pulsars. It's just that the light is sometimes pointing towards Earth and sometimes not because the star is spinning. Okay, last scenario, the death of a star. What happens if we have supermassive stars? Okay, supermassive stars also erupt in a supernova. And then so you got fusion of iron into the higher, heavier elements. And then you have these great big neutron stars. But there's a huge amount of mass there, packed into a tiny, tiny center. And so now the gravity is so huge, it creates a black hole. So let's kind of break that down a little bit more. Let's say the neutron star is this big. And then its own gravity compresses it so that now, if you could see it, it's only this big. And it used to be this big. But now it's a black hole. Well, if you measure the gravity, the gravitational force at this spot and this spot, the gravitational force is exactly the same for the neutron star and the black hole if you're the same distance away from the center. But now for a neutron star, you can't get any closer because now you're standing, if you could stand under these severe gravitational forces, but you can't get any closer to the center of the mass. But if you have a black hole, you can get, well, theoretically, you can get closer. And remember the equation for gravity, force, divided by the square of the distance. And so it's inversely proportional, meaning that if you can get closer, make distance smaller, then force will increase. And that's what we're doing. If you can get even closer to this huge quantity of mass, the gravitational force is going to get really huge. And it turns out that light can be pulled or bent by gravity. And you can reach a point where the gravitational force is so huge, even light can't escape. Let's think about trying to escape from the gravity of planet Earth. And we got this cannon placed on this block here. And if we shoot this cannon at 11.2 kilometers per second, well, that velocity would just match that required to put the cannonball in orbit. And if you go a little bit farther, then the cannonball will be going fast enough to escape Earth's gravity and go into outer space. So 11.2 kilometers per second. The sun, although it's much larger, is much, much more massive. So on the surface of the sun, there's a huge amount of gravity. And so now to escape from the surface of the sun, something has to be traveling at 618 kilometers per second. But at a black hole, the gravitational forces are just phenomenal. So that there's a certain distance away called the event horizon, where at that distance from a black hole, the escape velocity is equal to the speed of light. 300,000 kilometers per second. And if you happen to be closer than the event horizon, if you're closer to the center of the black hole, you have to go faster than the speed of light in order to escape the gravitational pull. And nothing we know of can go faster than the speed of light, so nothing can escape. Here's some artist renditions of black holes, showing material being sucked into a dark region. Since the center can't glow, none of that light can make its way out. It's going to be pulled back into the black hole. Okay, here's a nice little chart showing a summary of the life cycle of the star for low and medium mass stars, as well as for high and supermassive stars. So depending on their mass, you either get white dwarfs, neutron stars, or black holes. Okay, that's all for now. I'll see you in class.